Hi class, this is a review of areas that I did on Friday. Felt like we were cut a little bit short, so I wanted to give a little bit of a summary before you had to do your homework. One little note, I think from assignment number 1, I think numbers 1 and 2 you must do by the calculator because we can't do the antiderivatives. So actually only 3 and 4 you would do by hand. 5 and 6 you would also do by the calculator. 7 through 13 you would do by hand. And then in homework number 2 you can, or sorry, homework number 3 you would figure that out based on the directions. So I'm going to look back through the notes that we had. We talked about just bounded area between the curve and the x-axis is a simple integral. And then we actually went into doing the area bounded between two curves. And so up top, your note should say that the area is equal to the integral from a to b of your top function minus your bottom function. And remember, the key is to put square brackets around the bottom, dx. What we didn't get to is the fact that the area is also equal to from a to b of the right function minus the left function dy. So this one is in terms of y. And we'll talk about that a little bit more towards the end. I'm going to review the steps for finding the area in between curves. If you're doing it by hand, the first step is to find intersections. And if you need a little bit of help, maybe a sketch, if it doesn't take too long, it can be really helpful. Second step is to identify top and bottom functions if you're doing a dx problem, and then right and left functions if you're doing a dy problem. And then step 3 is the actual integral from a to b of either right minus, sorry, I should say top minus bottom first. Okay, top minus bottom dx, or a to b of right minus left for dy problems. So first thing I'll do is kind of review what we did for example 2. We ended up simply realizing that y1 was your top function and y2 was your bottom function, and we did find the intersections together. The intersections were at -1 and 2, and this is how we know we're doing a dx problem, because if I were to draw my representative rectangles, kind of like doing rams, they look like the rectangles you're used to. They go up and down. The reason why I only have one integral is because if you look, the top and bottom functions, they never change. The top function is always y1, the bottom function is always y2, and so this would be y1 minus the function y2 dx. In looking at number 2, in this case, this was the problem we did where we actually needed two integrals, because if you look, this rectangle, the top function is the function root of x. The bottom function is actually the x-axis, which is y equal to 0. Over here, though, in blue, our top function is still root of x. Problem is our bottom function changes to y equals x minus 2. And so because of the change, which occurs at x equal to 2, I'm going to need two integrals. So down here, our first integral will go from 0 to 2, the top function being root of x. The bottom function being 0 means that we don't really need to write it. The left side of the picture, which I'll just shade with a bunch of red lines, this side is actually just the definition of an integral, the area bounded between the function and the x-axis, and it is a signed, net signed area. In blue, we're going to add on the integral from 2 until 4 of the top function being root of x, but now the bottom function is x minus 2, and let me change that to a square bracket, dx. So that is a problem where you'll have two intervals. There was one more we had that looked like this, and f of x is your cubic function, so that's your red function, which I should probably put in red. And g of x is your blue function. So for this one, your integral, so the area bounded between going from -2 until 0. So what am I doing right now? I'm doing this area first, which is the red function, f of x, minus the g function, dx. Now, if I want to do the green portion right here, the top and bottom actually change, which causes us to have plus the integral from 0 until 2. Top function is now g of x minus the bottom function being f of x now. And what I want to be clear on is that you essentially are solving this like two different problems, and then you'll add the two integral values together in the end. I'm going to spend more time really looking at how to set up the problem, and I'm going to hope that the integration process you should be very familiar with at this point. Please don't forget to find your antiderivative first before evaluating f of b minus f of a. So this was the example that we ended with in class, so I'll walk through this one a little bit slower. First of all, we did this same exact problem using two integrals. We did an integral up to here, and then we had to change over and do another integral because the top and bottom function switched. Okay, so in the red section, the top function was root of x, the bottom function was the x-axis, but in the orange area, the top function was root of x and the bottom function was x minus 2. What we're going to see is we can actually accomplish this by doing a dy problem. So first thing I'm going to do is actually steal this picture and turn it. So what I'm going to do is turn it on its side. And so essentially what you're doing when you decide to do a dy problem, you're kind of supposed to turn your head so that you're looking at the function kind of on its side. So what I want you to relate this to is the fact that you're still going to look at the highest, so top minus bottom, but when we do a dy problem, we're actually going to go side to side. And what that causes us to do is draw our representative rectangles horizontally. So these are the rectangles that would be representative of us trying to find our area. And what you'll notice is that when you do this, all of our rectangles start at the same function and end at the same function. Now, things that you have to realize when we look at x values, they increase to the right. What that means is that the larger x values are to the right and the smaller x values are to the left, which is different than top to bottom. So what I did was I turned this picture onto its side. We could essentially consider this the top function, and we can consider this the bottom function. And when you look at it on its side and you draw your rectangles this way, it makes sense compared to what we did before. What we have to now do is really do this in terms of y's, and what that does for us is, first of all, we're only going to need one integral to accomplish getting the area for this. Secondly, we're going to look at this function in terms of right and left. So the major thing that I want to talk about is the fact that the steps are all the same, except we're going to sneak an extra step in the beginning. We're going to first need to solve each equation for x. What that does is it puts equations in terms of y. Step 2 is when you go back into what we were looking at. Step 2 would be find your intersections. Step 3, we would identify right and left functions. Right is our largest and left is our smallest, and that's why we do right versus right and left instead of top and bottom. X values go right and left. So in order to always have a positive area, we have to do right minus left. And so the fourth step is the integral from a to b of the right function minus the left function, d, and this time, notice I put dy. So some things that are going to be really important when we do example 4 is that we really want to look at the fact that we will be needing everything in terms of y. And what I mean by that is, let's see if I can get this to work. Okay. Everything is in terms of y. So first thing I'll do is I'll take this function and solve for x, which will give me y squared is equal to x. This one we get y plus 2 is equal to x. So both of these functions are in terms of y. Secondly, let's go through and find our intersection, which I'll do up top in red. Y squared is equal to y plus 2. Y squared minus y minus 2 is equal to 0. Y minus 2, factoring right now, and I get that y is equal to positive 2 and y is equal to negative 1. Now, the thing is, we just bounded ourselves in the first quadrant, so we're not even going to look at negative 1. So we're going to start our graph at 0, and we're going to go all the way up to a y value of 2. Okay. In step number 3, we're supposed to identify our right and left functions. The reason why we're using right and left is because we're doing this in terms of rectangles that are horizontal. We do top minus bottom when our rectangles are vertical. The top comes first because it's the bigger values, and for these rectangles, the bigger value is always going to be the right function, which is over here. The left function is the y equals root of x. So my integral will go from 0 to 2 of the right function, which is y plus 2, minus the left function, which is y squared dy. What you have to remember is this has to be a y value, and this has to be a y value. They cannot be x values, meaning you can't do this integral from 0 to 4. The point that's here up top is 2 comma 4. We're not allowed to, 4 comma 2. 4 comma 2, and we're not allowed to use the 4 because it's an x value. So in case you're confused on how you would do this problem, you would still just find the antiderivative, which would be y squared over 2 plus 2y minus y cubed over 3. You would identify f of 2. So it actually doesn't matter that these are in terms of y when we're evaluating the integral. So we have 4 squared over 2, which will give you 4 over 2, plus 4 minus 8/3. F of 0 is equal to 0. Therefore, the area bounded between those two curves is 6 minus 8/3, which is 10/3. What's the major key that you have to remember when integrating with respect to y? Key points? The key point is that everything must be in terms of y, and even the bounds. You can always choose to try and do every problem as a dx problem, but you may get some functions where they will give you the function in terms of y, and you will not be able to get the y value by itself. So that's kind of part of the reason why we do this. Also because for some of these, in all honesty, it's just easier to do them as dy problems. So this is one where I am giving you the function in terms of y. How is that obvious? Look right here. That means in terms of y. Okay. Find the area bounded between the curves. And so I am going to show you what the picture does look like, the graph. If you have no idea how to graph this, you are essentially doing a table. You're going to be stuck doing a table. I'm going to show you what this graph looks like to save a little bit of time. And I'm going to steal this back so that we can use it in the problem before. So here's what the graph looks like. I'm going to darken in the curve a little bit. Okay, so g of y is actually a parabola facing left because it's negative and shifted to the right 3 units. F of y is a line. And so what we're looking at is to find the area bounded between the two curves. I'll show you the reason why we don't necessarily want to do a dx problem. The first reason, they gave it to you in terms of y. The second reason, let's look at what this graph looks like if you try to do a dx problem. So when you look at my representative rectangles, everything's fine. The top function is the dark black, the bottom function. But what happens towards the end, and let me darken the curve again, is when you get to right beyond this point, you are stuck doing the area bounded between the curve itself, the top half of it, and the bottom half of it. This portion in here, the top function and the bottom function, don't match the top function and bottom function over here. In green, you would have to do one integral. In yellow, you would have to do a different integral. And the other problem would be that you have to realize that this actually has 3 functions total. This bottom half is the negative square root of that function, and the top is the positive square root of the function, 3 minus x, and you're causing yourself to have a total of 3 functions you're looking at. Now, I can show you this one really quickly. You would do an integral from -1 until +2 of the line, which is x minus 1, minus the bottom half of the square root function, dx, plus the integral from 2 until the vertex, which is at x equal to 3, of the top function, which is the root of 3 minus x, minus the negative square root of 3 minus x, dx. I am showing you the fact that it is possible to do the problem as a dx problem. It is confusing to most, the fact that the square root shows up and the fact that you have to use 2 separate functions to represent g of y equals 3 minus y squared. So I am not in favor of using that method. I would actually prefer to do it as a dy problem. So why is this easier as a dy problem? If I draw my representative rectangles, your top function and bottom function are no longer used. We're going to look at right and left. The right function is the parabola. The left function is the line. In this case, we only have a total of 2 functions to look at. When you write these functions in terms of y, it gives you a full parabola that happens to be a relation. If I wanted to write the function in terms of x, you get stuck with 2 different functions. And so that is one thing that makes this very different. I'm going to assume that some of you right now are probably confused, and you want to make sure you understand that, kind of like a circle, this parabola, to write its equation in terms of x, the blue parabola is written by the function up top. The pink parabola down here, the other half of it, is written by the pink equation down here. Similar to how we do circles, the top half of a circle and the bottom half of a circle. So what we're going to look at is the integral bounds would have to be y values. So I would suggest crossing out your x values so you don't even look at them. This integral goes from a y value of -2 to a y value of +1. So now we're going to look at the right function versus the left function. This is our right function. The line is our left function. And this problem would be 3 minus y squared minus the function y plus 1 dy. And the second you see this dy, double check, is everything in terms of y? Is that a y value? And is this a y value? You want to double check that before you move on. That is a major mistake I see. So in this case, everything is in place, and so you would essentially just be solving this simple problem, which, remember, the brackets are there so that we don't forget to distribute our negative. That was the whole reason of us having the brackets. Minus y minus 1 dy. And that would be finding the area bounded between these curves, given that you want to do the problem in terms of y. So hopefully this is helpful. Again, your homework, numbers 1 and 2 from homework number 2, you can use the calculator, meaning FNInt. We can also talk about how to do this in the calculator, as that usually becomes an issue. Surprisingly, if I was to do this problem in the calculator, your y1, you would actually write the function with x's. So you're replacing all of your y's with x's, and this can get a little bit confusing. Your calculator is going to calculate this completely differently than what you would think, because for you, you're probably looking at those as y's, and you figure, how am I supposed to type a y into the function? In y1, you're actually going to write x plus 1. In y2, you're going to write 3 minus x squared. And to find the area, you would do FNInt of y1, y2, which is the right function. This is y2, minus y1, the line, comma, x, comma, -2, comma, 1. I do understand that we have our problem by hand done in terms of y, but the calculator, you literally write it as though those y's are x's, but you have to already know what the integral statement looks like, and then you write it into the calculator, assuming that all of our y's are actually x's. I am sure I confused some of you, so please come in Monday and ask a question if you don't understand how to properly put a dy problem into the calculator. Otherwise, please make sure that homework numbers 2 and 3 are done for Monday. Thanks all.